Now, I'll discuss how we achieve the fastest BERT training time using DeepSpeed. In particular, DeepSpeed is able to train the BERT large model in 44 minutes using 1024 NVIDIA V100 GPUs in DGX2 boxes. This is 23 minutes faster than the previously reported time of 67 minutes by NVIDIA, where they use the same number and generation of GPUs. The table here shows how DeepSpeed scales as we increase the number of DGX2 boxes. So for example, on a single DGX2 box, which contains 16 GPUs, DeepSpeed is able to train the BERT model in just over 33 minutes. Moreover, DeepSpeed scales roughly linearly as we increase the number of DGX2 boxes, leading up to the 44 minutes training time on 64 DGX2 boxes. In terms of the techniques that enable DeepSpeed to achieve this results, there are two classes of techniques. The one class targets single GPU performance, and these are the efficiency optimizations. And the second class of techniques are the effectiveness optimizations, which target convergence tuning in a distributed or large batch scaling scenario. For the single GPU optimizations, basically two classes as well. We've developed optimized kernels for transformer computation, and this includes the kernel fusion and invertible operations. And the second class of single GPU optimizations are the model changes, the model optimizations, which include overlapping I/O with computation and exploiting sparsity in the output processing. Collectively, these single GPU optimizations enable us to achieve over 50% of the peak throughput of the V100 GPU. In the effectiveness side, the techniques here include mixed sequence line training, because we're training on a batch size of 64,000, pre-layer normalization, LAMB optimizer, and learning rate schedules. Collectively, these techniques enable us to converge using just 82% of the data samples compared to the baseline. So now I'll start with the single GPU optimization, specifically kernel fusion. The figure here shows the transformer computations in BERT, and specifically the colored boxes show the sub-computations, such as the query, key, and value gems. And each one of these sub-computations requires a kernel call for execution. And since kernel calls themselves come with an overhead, one of the benefits of fusing these kernels together is to reduce the overhead of kernel invocations. Secondly, when we fuse these kernels together, we increase the amount of work that's done within each kernel, and thereby we're able to improve the GPU utilization. Also, by fusing kernels together, we're able to reduce the amount of memory access to global memory, Thereby, we improve the data locality and simultaneously reduce the memory bandwidth requirements to the global memory. In BERT, we identified two classes of kernels that can be fused. The first class are the parallel kernels, such as the query key value gems, which execute independently and therefore can be fused easily. And then the producer-consumer kernels, such as the residual input to dropout and the normalization, which takes in the output. This can also easily be fused together. So as an example, let us examine how we fuse the QKV, or the query key value gems, and the corresponding transform kernels. And in this fusion, we'll be highlighting how they help to improve data locality and reduce memory bandwidth requirements. So the figure here on the left is showing the typical query key value execution in a normal PyTorch. Here, the forward pass, data flow for the forward pass is highlighted with the blue lines, while the data flow for the backward pass is highlighted with the red lines. And on the right-hand side is the fused version that's done by DeepSpeed. Here we see that during the forward pass, the query key value have all been fused into a single kernel, and on the backward pass, the transforms of this gems have also been fused. And what I'd like to draw your attention to is that in terms of the reads and writes that are done by these kernels. So if we consider first during the forward pass, we see that on the that the query key value all individually read from global memory, so there are 3 reads. But once they are fused together, this can be reduced to a single read. Similarly, on the backward pass, the kernels also make 3 writes to global memory in the default case, but after fusion, this can be reduced to a single write. The second class of GPU optimizations are the invertible operations. So invertible operations are operations for which we can compute the gradients without using the input activation values. And we're able to do this by just algebraic reformulation of the gradient computation. The benefit of invertible operations is that they help to reduce the activation memory footprint, because during the forward pass, we no longer need to save the activation memory for the backward pass. And the transformer, we identify 2 classes of operations that are invertible in nature: the softmax and the layer normalization. To illustrate, let me talk a little bit about the invertible softmax. Here on the left hand side, we show the softmax computation graph in normal PyTorch. And the thing to keep in mind here is draw attention to is that the gradient computation here is dependent on the inputs x1 through xn. So therefore, during the forward pass, we need to store this activation so that they can be used during the backward pass. But in DeepSpeed, by exploiting the invertible nature of the softmax computation, you can see here that the gradient computation is no longer dependent on x1 through xn, and thereby we don't need to store these activations, and that way we can save memory by avoiding the memory footprint of storing the activations. The other single GPU optimizations that we have, as we discussed earlier, are done on the model level. And so in particular, there are 2 classes. The first is the overlapping of I/O and computation. And here the idea basically is that while the GPU is processing the current batch, we can prefetch the next batch into CPU and perform all required pre-processing steps such as the tokenization and others. And by doing this, we're able to avoid doing the data loading from disk, and the tokenization and other pre-processing, we can avoid doing those on the critical path. The other class of optimizations we have are the sparse output processing. So we observed that in the output of BERT, the loss is only computed on only 15% of the output tokens. So all the other tokens are basically discarded. And so by leveraging this observation, we're able to reduce a number of computations that take place on the output tokens, such as projecting from the hidden dimension to the vocabulary size, and then running cross entropy on this output tokens. So overall, we're able to reduce these computations by 85%. And this is illustrated here, where we show basically the output tokens on the hidden dimension and the sequence and batch dimensions. By leveraging the fact that we have a mask that tells us which of these tokens are required, we're able to shrink the output by 85%. And using all of this, we're able to improve the single GPU performance. So now let's consider the impact of these optimizations on the single GPU performance. First, let's start with the sequence length 128 phase of the training, or some might call it phase one training. Here, this figure is comparing the performance of DeepSpeed with NVIDIA and Hugging Face kernels. On the x-axis, we have the microbatch size. On the y-axis, we have the throughput, first in samples per second, and secondly in the hardware throughput in teraflops. There are 2 observations that we can make from here. The first is that DeepSpeed is able to train with larger batch sizes compared to the baseline, in fact, up to 80% larger batch sizes. The second observation is that DeepSpeed is trained with a higher throughput, 26% faster compared to the baselines. Now let's consider the sequence length 512 training performance. Here our observation is that DeepSpeed is still able to train with 80% larger batch sizes compared to NVIDIA and Hugging Face, and the improvement, the speed up here is 28% in terms of higher throughput compared to the baselines. Now we move on to the effectiveness optimizations. These are the optimizations that target the convergence for large batch scaling. So the first class that we'll look at is the layer normalization. So layer normalization is a technique that is applied when we train with very large batch sizes to improve the training stability. It helps to avoid vanishing and exploding gradients. And so there's a key choice to be made here in terms of where the normalization is placed. There are two options. One is you could place it before the attention layer, the attention module, which is known as pre-LN, or you could place it after the attention, which is known as the post-LN. And here we illustrate both the pre-LN and the post-LN here. And the placement really has an impact, really affects the ability to train at the batch size of 64K. So as the figure here shows, we see that with the post-LN, the model actually diverges as we train, whereas with the pre-LN, we're able to train effectively and avoid divergence. The second class of effectiveness optimization are the LAMB optimizer and the learning rate schedule. And here the thing to point out here that LAMB optimizer enables us to do layer-wise gradient adaptation, which is also very important when you're training with very large batch sizes. And the customization we made to the standard LAMB optimizer is we made it configurable for users to specify the min and max coefficients. The figure here is showing the histogram of the gradient coefficients when training in the sequence 128 and sequence 512 phases of the training. And here we're showing the actual coefficient setting that we use for our training, which is we set the min and max to be between 0.01 and 0.3. The learning rate schedule that we use is a cyclic schedule with decay, and the key thing to just point out here is that we do a re-warm-up as we switch from the first phase to the other, from the sequence 128 phase to the sequence 512 phase. We observe that doing this re-warm-up is very important for training stability, otherwise we're not able to converge as fast. And so in summary, we're able to achieve the fastest training time for BERT model using DeepSpeed. And we're able to do this using two classes of optimizations that are independent and therefore have a multiplicative effect. The first class of optimizations are the efficiency optimizations that target single GPU performance, in which these optimizations enable us to exceed 50% of the V100 peak throughput. The second class of optimizations are the convergence tuning, which enable us to train to converge with roughly 82% of the data samples compared to the baseline. And the great news about these optimizations is that they can widely be applicable to other transformer models beyond BERT. Now we'll switch to the next example model, which is an RNN-based production model known as RScan. So RScan is a production model used in Bing to measure similarities between query and passages. RScan is based on bidirectional RNNs, as shown here in this figure. So here we see that the query and the passage are fed into hybrid embeddings, which include in convolutions. And this embeddings are fed into a bidirectional RNN, which then feeds into a residual classifier to generate the final output. So the objective for our scan was to scale it up to use multiple GPUs effectively in other words, to speed up, to enable faster convergence to the target AUC score. This AUC score had already been achieved on a single GPU baseline. And so the goal was to see how well could DeepSpeed help to speed up the convergence. And the high-level result was that with DeepSpeed, we're able to achieve over a 15x speed up on 8 GPUs compared to the 1 GPU baseline. To explain this superlinear speed up, I'll use the table that I presented here. So the speed up table is comparing the baseline 1 GPU, the baseline 8 GPU, which is basically using some off-the-shelf parallelization technique, and then the DeepSpeed 8 GPU. And there are 3 columns in terms of the speed up results. So the first column talks about the efficiency, which is basically how fast is the system processing data samples. So this is in samples per second. And here the baseline, of course, is 1x. The baseline 8 GPU achieved a decent 5.8x speed up, but with DeepSpeed, we're able to achieve an 8.7x speed up. And I'll go into more details a little bit later in terms of this results. The second column is the effectiveness speed up. And so here, what we're looking at is how many data samples did it take to achieve the target AUC score. And here, the baseline achieves it is basically 1x. The baseline parallelization technique did not achieve the target AUC. So in other words, even though the model was running faster on 8 GPUs, it was not converging to a satisfactory performance, and therefore it was pretty much not very useful. Whereas on DeepSpeed, not only are we able to match, we exceed the effectiveness, the baseline 1 GPU in terms of effectiveness. So we're able to converge using fewer data samples compared to the 1 GPU case. And this efficiency and effectiveness techniques are orthogonal, right? So one is basically talking about how fast are data samples being processed in the system. The other is looking into how many data samples it takes to convert to an acceptable model performance. And so these two can be combined together to get the wall clock speed up, which is we can look at that as how long in time does it take to get to the acceptable performance. And here, for the baseline 1 GPU is 1x here, the baseline 8 GPU is basically 0 because it never achieved the target AUC, but with DeepSpeed we see that it achieves it in over 15x faster compared to the 1 GPU baseline. So let's break down this superlinear speed up of DeepSpeed on our scan, starting with the efficiency improvements. So the efficiency improvements collectively give a 8.7x scaling, and this comes from both compute and communication optimizations. The compute optimizations provided 29% improvement, and this essentially comes from custom kernels that we wrote to improve the execution of a single GPU. The communication optimizations which provide close to 7x scaling, come from a custom all reduce, which helps to reduce the overhead of doing an all reduce during execution, and then exploiting sparsity in the gradients during the all reduce. So let me dive a little bit deeper into the sparsity optimizations by starting here with showing what we'll consider the dense representation for gradients. So imagine we had a 2-dimensional tensor here, and here we see 14 gradients that are about to be reduced. So the first thing we exploit here is observation that some of these gradients are actually zeros, and this corresponds to weights that are not going to be changed, and this would typically be true for things like embeddings. And so we can exploit the sparsity here by basically eliminating the zeros so that we don't have to be transferred over the wire, and thereby we can shrink the size, the payload of the all reduce. And this is what we've done here, and we convert this into things called index slices. So we need the indices to be able to remember which values are all zeros and which gradients need to be updated. Then the next observation that we made from index slices is that some of these gradient updates are going to the same parameters. And so, in other words, there are duplicates in our gradient updates, and that's true because in the same model, the same parameter might be updated multiple times in a batch. And so, what we do next is to deduplicate the gradients. And here we've highlighted in color that we have just three unique model parameters that are being updated by these gradients. We exploit the fact that gradients are basically added in, so it's a sum, and so we can deduplicate this and reduce that into the unique set of gradient model parameters that will be updated by gradients. And by this exploiting sparsity, we're able to go from a dense representation, which had, in this example, it had 14 gradients, and shrinking down to basically just 3. And so these optimizations collectively provide close to a 9x scaling compared to the single GPU baseline. So now we switched over to the convergence optimizations, which collectively bring us 1.8x improvements in the training time of our scan. The challenge here is that as we train on more GPUs, which means that we train with larger batch sizes, convergence tends to slow down. So in other words, it's been observed that as you scale your batch sizes up, your convergence slows down. And the reason for this is that your model gets updated less frequently compared to the smaller batch size. So for example, if you're training on 8 GPUs, your model will be updated 1/8 as frequently as if you were training on a single GPU. And this comes from the fact that usually when you've tuned your model to converge well on a single GPU on a smaller batch size, the set of hyperparameters that were found to be optimal for the small batch size case are rarely ever optimal for the large batch size case. And so to address this, solutions have been proposed, such as scaling up the learning rate linearly as you scale up the batch size. But fortunately, this does not always work. Sometimes it leads to slow convergence, or it could actually lead to the model divergence. And so we illustrate this challenge here with the figure here, where on the x-axis we're showing the data samples for training, and on the y-axis we're showing the AUC, which is sort of the the performance metric for the RScan model. And the goal here is to see how many samples does it take for RScan to convert to the target AUC. The gray curve shows the 1 GPU baseline, and which we see converges to target AUC in about just under 15 million data samples. The blue curve shows when we scale onto an 8 GPU training, but using the same, and we linearly scale up the learning rates. And here we see that even though the model does converge, it requires more data samples to converge, which is not acceptable. And then when we scale up the learning rate even more to see if that could help to converge even faster, which is a red curve, we see that the model just simply diverges. So to address this challenge of convergence for large batch sizes, in DeepSpeed, we use adaptive hyperparameter tuning. The basic idea here is that important hyperparameters such as learning rate and momentum should not have a fixed value throughout training, as will be done typically, but rather these hyperparameters should be adapted, should be changed dynamically to adapt to the different phases of training, of different phases that the model goes through during training. We've implemented the cyclic schedule that has been proposed in literature. We implemented a variant of that known as one cycle with decay. We've implemented this for the learning rate and for momentum. And this we found to be effective for enabling RScan to converge faster on 8 GPUs compared to the single GPU baseline. We show the results here in this figure. The green curve corresponds to the cyclic schedule on 8 GPU, comparing with the gray curve, which is the baseline on single GPU. We see here that DeepSpeed RScan with cyclic schedule converges in just under 8 million samples, which is almost half of the data samples required by the baseline 1 GPU. To give you an idea of what the cyclic schedule looks like, we show here the learning rate schedule. On the x-axis, we have the data samples, but in this case, we're presenting it in log scale. And on the y-axis, we have the learning rate values that are used at different points during training. The green curve is the cyclic schedule, and as we can see, it starts out from a particular learning rate value and increases over time until it hits a peak, and then it declines in a cyclic fashion. And when it declines to a minimum, it then starts to decay as time goes on. This can be compared to the other curves there, which shows sort of the fixed learning rate settings that is typically used. So the gray curve, for example, corresponds to the single GPU baseline. The blue curve corresponds to the baseline on 8 GPU, where we used a linearly scaled 8 times higher learning rate, while the red curve corresponds to scaling even higher, which led to the model diverging. One thing to observe here is that even though the model diverged when we use a very high learning rate, it's not because the model could not sustain that, but rather it's because the model could not sustain it at every point during the training. So because we see that with the green curve, we train with a learning rate that's even larger than the red curve, which means that as long as we can intelligently adapt the learning rate values, the model is able to train with even larger learning rates, which enables it to converge faster when we use very large batch sizes. To conclude this section, I want to address some natural questions that are probably obvious to you at this point about how, when you're thinking of how to tune a one-cycle schedule for your model. So some of these questions are, how do I set the learning rate boundaries? In other words, what should be the mean and max learning rate that I should use for my model? What is my cycle span? Like how wide should my cycle be? And what's my decay schedule? Basically, how often should I decay and by how much should I decay? And DeepSpeed provides some tools to help the model scientists automate answering these questions. And one of such tools, which I'll focus on today, is the learning rate range test schedule. This is used for detecting the learning rate boundaries for your model. And basically the way it works is that we train the model and we increase the learning rate throughout the training until the model actually diverges. And the learning rate at the point just before the divergence is the maximum learning rate for the schedule. So in other words, this is the maximum learning rate that a model can sustain during training without diverging. And once we have the maximum learning rate, we can figure out the minimum learning rate. Literature's suggested that the minimum learning rate should simply be a fraction of the maximum learning rate. And the literature also suggested that a range between 3 to 10 is a reasonable factor for computing the minimum learning rate given a maximum learning rate. An appealing part of learning rate range test is the fact that it's very cheap. In other words, you only need a very small portion of your data samples in order to figure this out. And for our scan specifically, we were able to effectively tune a one-cycle schedule using less than 2% of the data samples. Here we illustrate the range test experience for our scan. On the x-axis, we have the data samples in millions, and on the y-axis, we are overlaying the AUC, which is the primary metric, with the learning rate values. And as you can see here, we see that we increase the learning rate throughout the training, and eventually the AUC falls at the point where the model is diverging. And the learning rate just before that point is the maximum learning rate that we use for training our scan. Secondly, we also sort of have an idea, see here that the cycle span is also defined here, because it basically tells us how long should we increase the learning rate in terms of data samples, which defines like how long should the increased portion of the cycle be. And since we use symmetric cycles, then this also defines how long the other side when the learning rate is dropping. In summary, DeepSpeed enables the RScan model to converge over 15 times faster on 8 GPUs compared to a single GPU baseline. These improvements come from two classes of optimizations that DeepSpeed provides. The efficiency optimizations deliver an 8.7x speedup, while the effectiveness optimizations deliver a 1.8x speedup. Because these optimizations are orthogonal and complementary, their effect is multiplicative, giving us the superlinear improvements in training. With that, we've come to the conclusion of this section of the tutorial. Thank you very much for your attention.